Hello again. Today we're starting to look at the Runga cutter scheme, a scheme you may have come across briefly before, but now we're going to derive it all thoroughly using Taylor series, and this is the first video of one or two on this topic. Okay, I'm going to hand over the board now. Okay, so last time we were doing stability analysis on Leapfrog. And I just want to try and summarize the results and compare them with the Ford-Euler method. So let's try and do a table. We have the method on the left hand corner here, and then we want to have the cases of decay, exponential decay, and oscillation. So we have the Ford-Euler, and we have the Leapfrog. And we know, we can fill in quite quickly the unstable cases. We know that Ford-Euler was unstable for oscillation. We also know that Leapfrog, because it had this computational mode, or this parasitic mode, is also unstable. So you can see how it's sort of a nuanced thing with numerics. It's not just a case of that Ford-Euler is always bad because it's first order accurate, you know, and then we're gonna just put another column here of the accuracy, so it brings together all the idea. So we know that Ford-Euler is first order accurate, but Leapfrog is second order. Then finally, these other boxes, we know that Ford-Euler was conditionally stable. Conditional, by conditional I mean that the time step delta t has to be sufficiently small, and equally Leapfrog was conditionally stable, and that's the thing we did last time. Remember the condition, I won't do that for Ford-Euler because we've done it before, but omega delta t was less than or equal to 1 was the condition we relied last time. So in this table, if you understand all the elements of this table, we're coming a long way. We've got the accuracy from Taylor series right at the beginning of this section of the module, and we've then got these conditions for the decaying case and the oscillation case, and sometimes it's unstable, sometimes conditionally stable. And you may remember the problem with the Leapfrog arose because it was a Leapfrog scheme, if you like. It gave a quadratic in the amplification factor. So is there a way of also, the question is whether, is there a way of are there methods that avoid leapfrogging, if you like, and a quadratic in our amplification factor? And the answer is yes, and that's where we're going to look in the next few videos or so, is these other ways. One solution is to improve accuracy via the right hand side of the ODE. What do I mean by that? Well, we've got this ODE, dx by dt is f of x. Okay, and so far we've tried to improve the accuracy by doing a higher order expansion of dx by dt. But there is another way of doing it, is to leave the form of dx by dt as it is and improve the accuracy by doing better evaluation of f. So that's what I mean is focusing on this right hand side. And then this is going to give what's called, depending on how you do this, it's either going to give you a Runge-Kutta method or Adams Bashforth. I'll just tell you the names ahead of time. Okay, so these are more sophisticated methods that focus on improving the right hand side. Okay, so that's what we're going to do next. Let's try and get better accuracy relative to Ford-Euler with the Runge-Kutta method. So let's start with the Runge-Kutta. And as I say, this is an example of a numerical method that's named after the people who came up with it. It was actually developed, if you're interested, around about 1900 by some German mathematicians called Runge and Kutta. But the interesting thing is this was developed before computers, right? So people did numerical methods before computers. They had figured out how to solve equations in a discrete way before doing computers. So they'd probably be astonished by the ease with which we can solve their method now in MATLAB, because obviously they didn't have that at their fingertips. So the essence of Runge-Kutta is we now instead evaluate f of x at a number of points within the time step, and thus, and I'll show you this, achieve greater accuracy and a left-hand side that just involves xn and xn plus 1. Okay, so that really is telling you the result before we get there, but this is a bigger picture of where Runge-Kutta goes. So the idea is that within your time step, we just break up our timeline into little breaks of delta t and delta t. With the Ford-Euler, so say if that's t of n, you're just evaluating f of x of n, which is just at that point in the timeline. With these more advanced methods, you're trying to, if you like, evaluate it in multiple points, maybe 2 n points, and so the Runge-Kutta is these solid lines, and the Ford-Euler really is just this first point. So you can see how it might make sense that actually, in a sense, what we're doing when we solve an ODE is we're integrating this function on the right hand side, integrating f of x of n, and if we evaluate it in more points within the interval, we get a more accurate integral. So the steps, there's a fair bit of derivation to get to the Runge-Kutta method, but I just wanted to give you the overall picture of what it's trying to achieve. When you run a Runge-Kutta method, it involves multiple evaluations of f and achieves greater accuracy. So now I want to go into the sort of derivation of Runge-Kutta, and I'm going to call it RK, and 2 means second order accurate. So we're going to use this lingo throughout. It's Runge-Kutta RK2 or RK4 if it's fourth order accurate. So we're trying to achieve the same thing as leapfrog. second order accuracy, but we're trying to do it in a different way. And the derivation involves comparing two Taylor series one numerical, if you like, and the other the true solution. Okay, so we have the true solution, we're going to compare it, and thus we're going to derive this method. So it's coming back to our Taylor series again. I told you Taylor series was important. It comes up in many different places in numerical methods. So it's a really important concept to come across. So we're going to consider the ODE dx by dt is now a function of f of x on t. We're going to maintain a bit more generality than before. So we're going to have it as x and t. So we've got a method that's flexible for all cases. So we're going to write down first the RK2 method. So I'm going to use a new board. So the RK2 method is this. Has 4 steps. 1, you compute K1, which is one evaluation of our function f of x of n and t of m. So this is really evaluating your function at the start of your time step interval. Then we evaluate xm plus a delta t k1, and then t of n plus b delta t, where a and b are yet to be determined. Constants. Or constants yet to be determined. So they're yet to be determined constants. So we're just writing general terms. But we can see what we're doing. We're extrapolating the solution somewhere. We anticipate that a and b might be less than 1 at this stage, but we don't exactly know what they are. But we're trying to find some. So basically, you know, we're finding values some way within the interval integrals. So then we can evaluate K2, which is f of x of n plus a delta x, or t of n plus b delta t. So basically, f somewhere in the interval t n to tn plus delta t. Okay. So we've had a first evaluation of f at the start of the interval. This is very much like your forward Euler, but now we're introducing another evaluation of f of a, and then within the interval. And then we can put it all together in the 4th step. We then have our x n plus 1 equals x of n plus delta t c of k1 plus d of k2, where c and d are to be determined. And I think this is a good place. I mean, sort of finished this a little bit early this time because there's still quite a bit of derivation to go. But the key points to notice is we've now got a method that uses n plus 1 and n rather than n plus 1 and n minus 1. So we haven't got the problem, the quadratic in amplification factor that we had with the leapfrog. And now we've got to determine what C and D is, but we can see what we're doing here is we've got C of K1 plus D of K2. We're combining two different evaluations to the right of the function. So these are they're two evaluations of f, if you like, of your right hand side. Just consider if C is 1 and D is 0, obviously that's not going to be the case for Runge-Kutta, we recover forward Euler. Because K1 is f of x of n, yeah? F of x of n t of n. So that becomes xn plus 1 equals x of n plus delta t times f of x n of t of n. So sometimes for this reason, the Runge-Kutta is sometimes called the modified forward Euler method. You know, I've been asking this question a few times now, is how we can improve on forward Euler. Well, the Runge-Kutta method is a way that has a seamless transition between the forward Euler method and higher order methods. So if you like, forward Euler is a special case of Runge-Kutta where we just have one function evaluation, and then higher orders of Runge-Kutta have more than one evaluation. I haven't shown you what these constants are, A, B, C and D. In order to do that, I have to construct a second Taylor series based on the true solution, or the ordinary differential equation itself, and then we can constrain these constants and come up with the methods that are commonly used. So that's what I'll do next time, but hopefully you've got this clear idea of what the Runge-Kutta is all about, and we'll fill in some more details next time. Okay, so thank you for your time, and I will see you next time for more on Runge-Kutta. Thank you. Bye.